Good morning, everyone. This is part 6 of 3.3 hydrocarbons. In this video, we are looking at this box on the third slide, the first one there. Hydrocarbons can exist as different structural isomers. The slide that we'll be moving on to says isomerism, which is slide 32, this slide here. So let's start that. So isomerism. It says molecules that have the same molecular formula, but have different structures. They are called structural isomers. So two substances which have got different structure but same mass, they are isomers of each other. For example, well, this is not an example yet. Here you have this dog-shaped molecule, which is actually eth with alcohol group. Hydroxyl group will give the ending of whatever O. So this is ethanol. Okay, two carbons with OL at the end. So ethanol. Now with this ethanol, there cannot be any isomers. Rule number 1: you can say twist things around. Well, this now looks like, it's attached to different position, but it can go back to this way, okay? Or if you chop off this ethanol's dog's neck and replace that with, replace the head position with the tail, and put the head into tail position, you haven't actually created anything new at all. You are just looking at the same molecule from different view. So ethanol itself cannot have any isomer to it. When it comes to this sea leaf dragon type of thing, 1, 2, 3 carbons with OL at the end, so it should be propanol. We will talk about functional group stuff and the naming of it after this video in a part 7. This one should be called 1-propanol. 1-propanol or propane 1O, because this group is attached to the first carbon. And by the way, even if you're counting the carbon chain from this end, that needs to be the first one. 1, 2, 3, 1, 2, 3. Even though you change the view of it, it needs to still be 1O, because they are the same molecule. Okay. Now, another important thing is you need to be able to do this in your head. You need to be able to picture and rotate around, upside down. You have to be able to do that to be successful in this part. Now, another thing that you need to also know is that this one, propane 1O, can be propane 2O. Never propane 3O though. As I said, propane 3O. When you try to make that, you're still having propane 1O. This is not 3. You have to give the lowest number. That rule doesn't change. Now, with this one though, you can chop off its neck and remove one hydrogen from the center carbon and put the alcohol group, hydroxyl group, on the second carbon. Hope you can see this. So 1, 2, 3, or 1, 2, 3. Either way you count the chain from, it's still 3, and OH group is attached to the second carbon. This is a isomer. This is an isomer of the first one. Now, namely, this is propane 2O or 2-propanol. So if you change the position where hydroxyl group is attached to, you would make that into isomers. So propane 1O and propane 2O, they are structural isomers of each other. Now, why does it matter? Now, you can find the molecule on just above me here. It says mirror image. There are two mirror images of enantiomers. They are also structural isomers. Enantiomers have show a different almost bend to it, like they are mirror image, but because of the bend, they are not considered as the same thing. It's like left hand and right hand. Even though they look kind of similar on the screen like that, but they are actually different. They've got different shapes. Why does it, yeah, what's the matter with them? Why are they so important? Now, because the molecule that you are seeing above, the left-hand one for you, is the effective medicine for morning sickness. So 1957, was it? Yeah, 1957. Somewhere around Western Europe, to Germany, around that area, this medicine called thalidomide was sold just over the counter to cure morning sickness. What they didn't know was that it was not refined enough, so it actually had left hand and right hand shape. Left hand one was very, very effective and cured the morning sickness. But the right hand one, as you can see in the diagram just above here, it caused birth defect. Now, if you are interested and if you want to take that, maybe look for some images of thalidomide babies. They came out with no limbs or just deformed shape of body, and some brain damage as well, I think. But well, it depended on the baby, case by case. But that caused a fair bit of issue. So they had to come up with a method of refining the medicine, so you can only have the left hand one and gotten rid of the right hand one. Although it was small amount involved, it was still enough to be able to cause some issue while the fetus was growing. Okay, so that's why it is important for chemists to know what sort of isomers can be possibly made. Yep. So that's why it's a SHE connection, science as human endeavor connection. All right, now let's do a bit of examples there. We're looking at 7 minutes. All right, so firstly, I'll do butane. So butane has got C4H10. That molecular formula cannot be changed if you are trying to draw two isomers. I should go this way. So first thing that you can do would be to just connect them together. So C4 is there. If you fill this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens can be placed around. I'm not going to draw that. That's going to take a bit longer. Structural isomer that you can think of would be, firstly, just do 3. And imagine that you detach that carbon and try to attach to somewhere. Now, if you attach this CH3 group to side this end, you're still having 4 carbon lengths, which doesn't make any difference to the first one. So I'll put that into the middle carbon in this 3 carbon chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You should be able to still have C4H10 as its molecular formula. So this one and these ones, this one, they are structural isomers of each other. We haven't removed or added any hydrogen or carbon to it. So yeah, the mass hasn't changed as well. Different structure, same mass. That's for butane. By the way, let's try naming them. So this was 1, 2, 3, 4. But is the prefix. No double bond and triple bond. So ane would be the ending, the suffix. Whereas this one, 1, 2, 3, whichever you count, 1, 2, 3. 3 is the longest carbon chain. So meth prop, it's the prefix. Do you see any double bond or triple bond? You don't. If you do that, you'd lose hydrogen. So still ane. But one thing you have to think about is one group of CH3 being a branch. Now, a branch with 1 carbon is methyl, meth with YL, and the position of that is the second carbon. 1, 2, 3, so second carbon. So you have to say 2-methyl propane. 2-methyl propane. That's the name for this compound. So butane and 2-methyl propane, they are the structural isomers of each other. Now, you might keep getting this next example of hexane. There are 5 isomers. Try making sure that you can recognize the longest carbon chain in everywhere. You can try putting methyl groups in second and second or third and third. They will probably give you different isomers too. Okay, as long as you can give different names, they are structural isomers. All right, have a go at it. I'll give you some time to do questions in textbook as well as the probably 2-3 worksheets. Okay, I will see you in class.